Yes, but this has already been a couple of years.
Shared reference frames.
Yeah, let's make a reference to a frame job for the new people, sure. Now, a logistical comment. I got 2 emails over the weekend that you still have a couple of exercises for me that I should upload, and I should. I agree. This weekend was the open day on Saturday, which took me the whole day, and on Sunday I had to go to Amsterdam, unfortunately for some family business, not of the good kind. Everything is fine, but I was sort of a couple of things on my mind this weekend. Anyway, so they will be uploaded, don't worry about that, and one of them I will actually do right here, right now. So far, the logistical comments, let's just see where we are in our narrative. You recall from the last couple of weeks, we started out by doing relativity the wrong way, yes? Then we went on to do it the right way, that was last week, and we got the full toolbox, yes? We got the full Lorentz transform, so we know exactly how to transform from one inertial frame to another inertial frame, even when in the 2 inertial frames, the 2 events. Good morning. No, that's fine, that's fine. As long as you find a seat, will be good. As long as some of the events happen at the same location or are measured at the same time, you can use your standard Lorentz contraction and time dilation. If not, you can use the full Lorentz transforms. So the full Lorentz transforms are going to be your best friend. If you recall from our first meeting a couple of weeks ago, I gave you this whole series of steps that we're going to go through, and you might recall that today we're going to do nothing new, really. I'm not going to teach you anything that you did not know before. The only thing that I'm going to do is teach you how to make things visual, how you can do the exact same conclusions in a graphical way. Yes. Now, all of this, exactly how to do the full toolbox of special relativity in a graphical and an algebraic way, is going to be the content of the midterm. Yes. On Friday, I will give you a little bit of how the midterm will look like, what I'm typically going to ask of you. It's not a tick-off list, yes, where I just say you get exactly this and exactly that and exactly that, but I'll give you some glimpse of what it will look like. So today is really the last new content as far as the midterm is concerned, and as far as physics is concerned, it's not new content, it's just old content written in a new way. There's something else, according to the narrative a couple of weeks ago. Today we're also going to do some of the paradoxes, right? That sometimes in relativity it looks as if things are not agreeing with each other. And we have found that if you do a little bit your best, especially if you take the full effects of relativity into account, that there's usually no paradox. If there is a paradox, 9 out of 10 times it's because somebody in your setup tried to apply the rules of special relativity where they were not allowed to begin with. Okay? So, 2 reasons for having paradoxes. One of them is either you did not take into account all full effects of special relativity, typically loss of simultaneity is what is missed, or the other one is one of your observers, one of your inertial frames tried to apply special relativity rules where they were not allowed. And I would like to start with the latter, actually. I'm going to do an exercise with you where you can actually see this happen in practice, yes? It is one of the exercises that I gave a couple of weeks ago that we did not do in the tutorial. It had to do with a particle being in an electric field. Do you recall this exercise? Maybe you've read it, maybe you've seen it, maybe you've done it. If not, that's fine, because we're going to do it right here, right now. Speaking of Jacco, he's going to talk about my field on Wednesday, tomorrow. So I'm going to take 20 minutes to talk about his, okay? Particle physics. We're going to start with a particle. And that particle is going to be accelerated from this point A, to some point B in the laboratory. The laboratory in this particular case means this particular frame on the floor, and for lack of a better word, I would just call it a lab frame. Now, do you know how they accelerate particles, typically? How do you give it a particular velocity? Give you a particle, I want you to give it a velocity. How do you do it?
Push in an electric field.
Sorry?
Put it in magnetic field.
A magnetic field.
I would have said electric field.
Okay, I hear electric and magnetic. I would like to hear for both of the options which one do you think is the correct one? Because one of them is correct and the other one is not, and I would like to hear the reasons why.
Well, the electric field accelerates, but with the magnetic you just make it go round.
That is, okay, there you go. Great. You might have picked up either in your high school physics or if you're going to follow the course in electromagnetism in period 4, not my course, but the course by Benedict Poser. One of the things he's going to teach you is that you cannot use a magnetic field to do work. And if you recall, work is just another way of saying that you supply energy to an existing situation. Yes, you cannot put more energy into something by doing a magnetic field. So that means you cannot make something move faster by the magnetic field. The only thing you can do is steer it in a different direction. Yes, I can immediately see that you have a question.
But couldn't, by changing the magnetic field, wouldn't you still be able to use Lorentz force velocity?
As in you go to a different coordinate system?
No. And if you just change the magnitude of the magnetic field, couldn't you still induce the Lorentz force that accelerates the particle?
The answer is still no. But the answer is yes and a little bit of no. But now we are sort of delving a little bit into not just electromagnetism, but electrodynamics. That is the course that I gave in period 4, where you have followed that course. You have not?
I have only done your general relativity course.
Okay.
Yeah.
Only my general relativity course. Okay.
Just the general.
Well, let's stick to the. I'm going to go into your question. If you're not going to pick this up, don't worry about it. If you want to know more, period 4 and such, electrodynamics. Yes. Short answer to this question was, how do you make this thing go in the first place? You need an electric field, because magnetic fields can only push particles into different directions. It cannot supply more energy. It's a very famous law in electromagnetism. Magnetic fields do no work, and work is just another way of saying supplying extra energy. Yes, magnetic fields cannot do that. So the only way that you can accelerate this, or in other words, give it more energy, is by putting an electric field over the thing. Now, of course, the only way that you can make that work is if the thing has a charge. It's much more difficult if you do it for neutrons or something like that. Yes, but if you have an electron or a proton, you can make this work. Now, short comment to Felix's question. He said, yes, but what if you have a magnetic field? So there is a magnetic field. The magnetic field might push the thing in a different direction, but you make the magnetic field get bigger and bigger and bigger. Yes? Can you then make it go faster? And that answer is actually yes. And that is because, and here's the electrodynamics part, a change of a magnetic field.
Yeah, right, that's smart.
It's yeah, well. Change of a magnetic field. I didn't come up with this, okay? This is all Maxwell. It's the 4 Maxwell's equations, okay? A change in a magnetic field results physically itself, is equivalent, physically speaking, to an electric field. So if I were to have a button here, a knob, and I can turn it open and change the magnetic field in time, I get a changing of the electric field as well. And therefore, for that particle, it is as if there is an extra electric field appearing, and that will make it go faster. So yes. But maybe I should have phrased my question a little bit more Felix-proof by saying a fixed magnetic field. Okay, now long story short, what you do, you put an electric field over this thing, yes? Now, you can make this thing go faster, but as you know, as the thing goes faster and you want to accelerate it all the way here till the end, you might ask yourself how much time elapses for this particular thing, for this particular charged particle. The question in some cases is not super interesting, but if you are a particle physicist like Jacco is, then it is interesting because you need to know what happens at what time as seen in the particle frame. But you, in the lab frame, are not measuring the same time as in the particle frame, so that means you have to do the conversion. There's one exercise in the book that lets you calculate for a particular accelerator, this is SLAC accelerator in the US, lets you calculate how much time passes for this particle in the SLAC, or let's call it the particle frame, as opposed to the amount of time in the lab frame. And the way that the exercise is phrased is a little bit ambiguous, because they don't state whether the particle is accelerating while you're doing the exercise. This should be not a difficult exercise for you if the question only is if it is a constant velocity, because then you know what to do, yes? So let's go over this very quickly. This is really just week 1 stuff again. So if I were to ask you how many seconds it takes for this particle to end up here. I'm not going to put numbers. I'm sure you can put in numbers in your calculator. That's not the point here. It's about the formulas and the application. So there's a distance d as seen in the lab frame from the beginning of the slack accelerator all the way till the end. So there's d. It's a nice check whether you're ready to do at least some of the exercises of the midterm of next week. You would first define two events, yes? What two events would you take? If I specifically phrase the question about how much time has passed from here all the way till the end.
From which frame of
The events are a frame of reference list.
Oh.
So particle is at distance d equals 0
Sure.
or at point A.
Particle is at A and
Particle
sure is a particle is at B. That's easy enough, right? You define your events. Now, if this is a particle that could actually decay into other particles, like a pion or something like that, that's a charged particle you can accelerate with an electric field if you wanted to, pi plus or pi minus. Pions will fall apart at some point, right? They will disintegrate. Then knowing the amount of time that passes as seen in the particle frame is very important, because the particle will decay when his own clock says it's time for him to decay. So it's really important for particle physicists like Jacco to have the time in his own lab frame compared to the time over there, because then he knows whether the thing will fall apart before it reaches the end of the detector. These sorts of questions. Now, we have our two events. That means we also have two moments in time. We have the, did I call that particle? Particle, and you also have an amount of time to go through these two events as seen from the lab. I'm sure there's some time dilation. Where does the gamma go? This all stuff that should be really easy for you now.
Particle.
Yeah? Why is that?
Because it sees both, like all the events at the same time.
Well,
Because it's
at the same station.
yeah, that's what I meant.
Yeah, but yeah, I mean, I'm sure you meant it, but make sure that you write it down correctly. Yes. The correct phrasing would be something like the two events, these two, happen at the same location as seen from the particle frame. So that means that amount of time gets a gamma. Okay, there you go. Now, depending on how the question is phrased, you can put the v in, you can calculate, you can see how many seconds, right? If they tell you that this slack accelerator, I have no idea how long it is, by the way, kilometer or something like that, probably less. Anyway, we can look it up. But if you know what this d is, you
2
can
miles.
just calculate. Sorry?
I think it says 2 miles.
It says
2 miles?
Yeah.
Okay, well, then make it 2 miles. You can also calculate how many seconds that takes in the lab frame to cross the 2 miles given its velocity. Yes, you can just use your high school physics, blah, blah, blah. You can do this exercise. Nothing we have not done before. Now, why am I doing all this trouble just to go through a very simple exercise from week 1? It's because I wanted to point you towards one of the misconceptions, right? This week is about the graphical way of doing these exercises, but also about the misconceptions and the paradoxes. Here is a misconception that you encounter frequently in special relativity. Somebody comes in, that's me, somebody who does not know much about special relativity, and he will say, wait a minute, this particle is accelerating. And special relativity only applies to things that go with constant velocities. So therefore, I should not have been allowed to use this formula in the first place. This exercise does not belong in a special relativity course if the velocity is not constant. There are many people who would think that that is the case. It's wrong.
Our measurement frame is still inertial.
That is correct.
Well,
You are allowed to use special relativity as long as you apply it from an inertial frame. It doesn't matter if the thing that you're looking at is accelerating or not. As long as you, the measurer, is in an inertial frame, you are allowed to use special relativity. So that means this calculation works beautifully well. Because look, I applied it from an inertial frame. Granted, if this guy is not a constant velocity and is accelerating in some way because of the electric field, it is certainly true that this guy is not an inertial frame, right? So that means if I were to do a calculation where I started from his frame and then try to calculate back to this amount of time, that will be wrong. As long as you are an inertial frame, you can use special relativity. It's only when you go to a non-inertial frame and try to do your relativity there, only then do you use general relativity. Now, for the people going to the general relativity, there's an additional statement. At the moment that you are in a non-inertial frame, that's going to be equivalent to having a gravitational field. So the statement is a little bit broader than this. If you are in a frame that is accelerating with respect to something that you know is an inertia frame, then you have to use general relativity if you want to calculate from this frame, and /or if you find that this particle is under the influence of gravity. Again, you will see in general relativity, if you're going to pick that course, that those two statements are actually the same. They're related to each other, but that's for then. The reason that I'm pointing this out is there's really lots of people, and exercises even, where they always say particles and objects are flying with constant velocity, and it might give you the impression that special relativity is exclusive to constant velocity situations. Now, if that were the case, Jaco would have a hard time in his particle physics on a daily basis. Jaco never uses general relativity when he does his exercises. And that's because the only thing that Jaco does is go from lab frame to particle frame and not the other way around. Not just Jaco, all particle physicists. It will be a very, very, a theory that has very little application if you can use it only for particles that go with constant velocities. Yes, it's like saying use Newton's laws, but only when things go with constant velocity. There's hardly a point in writing down mechanics. So, let's do this exercise now when we are assuming that the thing is accelerating, just to see how it's done. All right? Now, so we're now going to say that this particle accelerates. Now, given the exercise, you need to know how much it accelerates. So you need to know how v depends on t. Now, that of course is going to be highly exercise dependent. So, just for definitive sake, I'm going to say that it's a constant acceleration. And constant acceleration means that its velocity is given by its acceleration times the amount of time that it has been flying. Agreed? So this is just my setup of the exercise. I'm sure we can come up with exercises where Jaco already gave the particle a kick or increased the electric field as the thing went along, so it got more and more acceleration. That the acceleration itself is not constant in time, but in our simple exercise, we're going to take this A to be a constant. This is actually the way that they do it in particle accelerators. They have a constant electric field over their tubes through which they fly their particles. They don't have to, by the way. They can easily increase the electric field. They don't. First of all, the exercise becomes much more difficult. Secondly, there's no point, because if you want the particle to go faster and faster in a constant electric field, just give it a couple of extra seconds. Yes, but just be pushed and pushed and pushed. And thirdly, if you increase the electric field, what happens?
There's a magnetic field.
You will introduce a magnetic field because of electrodynamic rules.
Just bending your thing all over the place.
Yeah, that means that if you want to keep it flying through a straight tube or even a curved tube, and that means you're going to push the thing out of its tubiness. That's not a word. Okay, don't write that down. So for practical reasons, you stick to a constant electric field. Fine. So that means we're going to take this guy as constant. Now we have to be a little bit careful because acceleration, as you know, is an amount of distance, hand-wavingly speaking, divided by the square of an amount of time, but both of these numbers are going to be frame dependent, yes? The amount of distance and the amount of time is going to be different in the lab frame as they are from the electric frame, the particle frame. So you can do either, but you have to be clear which one you do. Now, pragmatically speaking, which one is the most handy to work with if you are Jaco?
Lab frame.
From the lab frame, right? Because those are the buttons you control. You're not traveling along with the thing. If you are Jaco standing in lab frame, then you're much more interested in the numbers as they apply in the lab frame than they are in the particle frame. So let's actually put lab here. And in very much the same way, the amount of time that goes by, in Newtonian physics, this amount of time will be the exact amount as this amount. But then again, we're not in Newtonian physics anymore. So you have to put somebody's time there. Now, two comments. First of all, if this is already given in the lab frame, then this is given in the lab frame as well. Otherwise, you have used the wrong definition for the acceleration. Secondly, if you are again Jaco and you're standing next to your particles flying by and you're keeping time, then you're keeping your time. So this is really, pragmatically speaking, the one that you need. Academically speaking, of course, you can also use the other guy's time, but it's not as handy. Yes?
What is this going to work out? Because eventually like it's just going to keep increasing, right?
Yes.
So in this part of the equation, you ignore relativistic effects because you're using the lab acceleration and the lab time. So
there's a good point there, yes.
Eventually you'll end up going faster than light.
There is a good point.
It's going to mess up the equation.
So I'm paraphrasing you. The point here is, wait a minute, if this were the rule, you will find that this guy, right, I mean this expression will tell you that at some point the particle will fly faster than light. We haven't proven that it's impossible, by the way. Tutorial comes back and back, right? So everybody says, no, but you gotta go faster than light. We haven't proven it yet. We will in 2 weeks. But let's.
It's the last thing we do.
No, I've given your tutorial at least 4 ways that this is true. Yes.
Yeah,
okay.
that's true.
But yes, let's already borrow some of those conclusions. If you write it down like this, it does mean that at some point you will go faster than the speed of light. Now, that is a subtlety that I'd sort of like to sweep on the rug right now. I can say a little bit extra about this.
Gideon.
No, that's fine. No, it's a good comment, right? This is really the physics, and you have to take care of this. Now, this lab acceleration comes from Newton's law. Just very briefly, and again, I'm just borrowing from 3 weeks from now, actually. This is Newton's law as it would look like in Newtonian physics. Yes. So you get something like this. And maybe you know from either your high school or your electromagnetism that the actual force that the particle feels is the charge of the force times the electric field that is applied on the thing. So I put EL there just to distinguish it from an energy or so. You will get something like this. Yes. And indeed, if this number is constant, that number is constant, and m is constant, the mass of the particle, you get a constant acceleration. And then, of course, you do end up that if you wait long enough, that you will make that particle go faster than the speed of light, which indeed is going to be impossible. The reason that that occurs here is because I'm applying a Newtonian rule to calculate the acceleration of the particle, whereas this rule does not apply in special relativity anymore. We will find in a few weeks that this is the new rule. You get Newton's law, but with a gamma to the third in front of it.
Spoiler alert.
Yeah. I wasn't going there, but you know, if it comes up due to a question, I'm happy to tell you. So we're physically going to prove this, yes? This is going to come out at some point. Now, a long story short, because of the gamma to the 3, do a very quick calculation. That means that a lab is going to be F lab over m divided by gamma to the 3. That's just an algebraic step. And because you know that gamma itself is 1 over the square root of 1 minus v squared over c squared, blah, 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 you get this. 1 minus v squared.
Is there an intuitive reason why it would be gamma cubed? Because gamma squared seems nice, but gamma cubed.
Well, if you relate the distances, length contraction, you have a gamma, then maybe velocity of squared, and then acceleration.
You can sort of hand-wavingly feel it happen, and I think this is part of the part. I mean, this acceleration is something like an amount of distance divided by a square of the time, if you will. Yes.
Yeah.
But all of these 3 come with an extra gamma. But this is very hand-waving, yes? This is not a proof. This is just thinking there's probably some extra gammas there because of time and space and everything. You have to do it more formally, and we will.
I know, but my logic was since velocity already only has 1 gamma, and acceleration would be...
Velocity is...
I can only say...
Okay, yeah,
okay. The point here is... No, it's a good question, though. Why a gamma 3 and not gamma 2? Again, hand-wavingly speaking, you can say something about, well, there's at least 1 distance and 2 times in there, and all of them come with a gamma, but it is very hand-waving. If you want to do it formally, this is why we're going to introduce Lagrangian Physics at some point. Now, long story short, if you have the A lab here, then this is the acceleration that the particle will get at any moment in time, given that you've given it this amount of force, yes? Now, going back to your first year calculus, I have a function v is a function of t, and I want to know when it obtains its highest value. How do you find a highest value of a function?
Equal the difference.
Yeah, exactly. You take the derivative, you set it equal to 0. Now the derivative of this guy is that guy, agreed? The derivative of a velocity is an acceleration. So if you want to know what the highest velocity is that you can get, you have to set the acceleration equal to 0. Question, if f lab is not 0 because your electric field is not 0 and m is not, well, whatever number it is, can you see here at what velocity the acceleration becomes 0?
Let's see.
At c. So apparently, if you accept for me that there is a gamma to the 3 here, actually, Felix, if you really want your gamma 2, the argument still holds. So it's not the power that does it, it's the fact that there is a gamma to begin with. You can see that the highest velocity, or in other words, when the acceleration is 0, happens when phi is a c, agreed? Now note that it doesn't even matter what the force is. We took a constant force in our example, but any force will be killed by this guy being 0. So that's another way of saying that no matter what you do, no matter what kind of force you try to apply to any particle in any setup, the fact that there's a gamma to any power here, it happens to be 3, but to any plus power, you will always end up that special relativity does not allow particles to go faster than the speed of light, no matter how long and how strongly you push or pull. That's what you see here. Now this argument is based on this equation, and for that, again, I have to ask you to wait a couple of weeks. Then I'm going to show you where that comes from. That is really a whole lecture by itself, but we will get there. Now, going back to Felix's comment, it's really like it's the questions. I mean, it's good questions is what I'm saying.
Yeah, really good.
Good. And I think they're helpful too, because I think, you might, when you study this at home, you might have come up with the same questions maybe. So Felix's point was, but wait a minute, this situation might have ended you up with an acceleration or a velocity of the particle that's faster than the speed of light. Yes. Now, I'm sort of smuggling here because I'm using a Newtonian way to write down how much the acceleration is. If you want to do it really fully relativistically, then this A lab should be replaced by this expression, which is correct. It's just mathematically going to be more cumbersome. Yes? So I'm going to assume that there is an acceleration. The acceleration might not bring you close enough to the speed of light that you have to take all of this into account. But it is relativistic enough for you to have some difference between the particle time and the laboratory time. It's a little bit hypothetical, yes? If you want to really do it correctly...
Can you say that sentence again, please?
Yes, I'm going to make things relativistic enough that this time is not that time. But not so relativistic that the particle will reach a velocity that should make you take this A lab into account instead of the constant one that I've been using now. So it's sort of like a middle ground here.
Okay.
Don't they just say that the velocity is 0.99999?
That's why they did it.
I'm sure. Well, the thing is, this expression is of course always true, right? There's no real cutoff point where you say, well, if v is smaller than exactly this number, you might as well drop this and get back to Newtonian physics. It's always relativistic physics. The question is, how much percentage, how many digits behind the comma do you care about? There's no cutoff point where you say, from this moment on, you should have used this equation instead of the other one. But suppose that Jaco is only interested within 5% or something like that. Then you can find which v corresponds to the situation where this guy and the constant one here only differ by 5%. So again, there's no cutoff point. It's highly context dependent what velocity you should take to justify using not this one, but a constant one. Anyway, my whole point here, so I'm going to take this matter as settled for now. The whole point here is that I'm going to take this guy constant enough that I don't have to worry about these extra effects that really should also come into play. Yes. If you want, please feel free to redo the exercise with that guy in. It's the same steps, it's the same physics, it's just mathematically more cumbersome. But it is correct. My whole point here, if you go back to the original question, was can you use accelerating particles, or can you use special relativity to describe accelerating particles? And again, one of the huge misconceptions of special relativity is you can only use it for things that go with constant velocity. But you can also use for accelerated velocities. Now, we have to be a little bit careful now. So I'm going to show you how that works. You have to be a little bit careful because I wrote here these big deltas, which accounts for the total amount of time going from here to there. But the electric field will make this particle have a different velocity along the way. In other words, the gamma that we had here will have a different value along the way, right? With every next second, the thing will have gone faster and gamma will have gotten bigger. So taking the full amount of time to go from A to B is not what you want. But what you can do is take an infinitely small amount of time. So that really is from this point, say, to that point. Very small amount of time. Why? Because during very small amounts of time, the velocity is approximately constant. Yes? An accelerated motion, you can see, is very small amounts of constant motion, but with every next moment, the velocity is slightly higher. If it bothers you that you think, wait a minute, isn't that cheating? Well, yes, but this is how we do this in calculus. This is literally what a derivative is, right? If you have a curved motion like this, then if you make your delta x very small, then over here it's like a straight line. And if you make your next delta x also a little bit small, then this is also straight line-ish. And at some point the straight lines will be different straight lines, but they will be straight lines. Derivatives, if you recall, is literally this. You take df, so how much this goes up, divided by dx, how much you went to the side, assuming that the amount that you went to the side is infinitely small. Right? That's the definition of a derivative. So we are going to do the same thing here. We're going to say that the velocity of the particle, even though it's accelerated, consists of very small patches of time where in each of them you can approximate the velocity as being constant. This is why I replaced the big capital deltas, which stays something about from here to there, by small d's, which means going from here to a very small amount of time extra. And during each of these little patches, take the constant velocity. So that means you can now write this, your basic time dilation formula, just as we did before, with the difference being that this time is now time dependent. Or excuse me, this velocity is now time dependent. So what do you get? Let's write out the gamma. 1 minus v. V, if you recall, is now given by this expression. Or if you want to replace this a by that one, I'm fine with either. You get a lab times t lab divided by c squared times the amount of time that the particle thinks that it takes to go from here to here equals the amount of time that Jaco thinks that the particle went from here to here. Yes? Good. We have an expression now for how much time it takes for the particle to go a very small amount of distance from here to here, as seen by Jaco and as seen by the particle itself. Now, originally the question was, how long does it take for the particle to go from here all the way to here? So here's a question from calculus for you. I have an expression for an infinitely small amount of time, and I want to have the full amount of time. What do you do in calculus if you want to take an infinitely small to a finite amount?
Integrate.
Integrate.
Integral from a to b.
So you integrate. Yes? So what you're doing, you're really just saying, okay, well, at first it's this, then you get a number. Then you're going to do the same exercise, but now for this distance, you get a different number, you add these two numbers. Then you're going to take a little bit amount of that distance, you get another number still, you add that to it, and you do the whole adding all the way till the end of the other side. This is by definition integration, yes? It means go over the x-axis and take all the little dx's and add everything together. That's an integration by definition. That's what we're doing over there. So you can perfectly do this exercise. Just take into account that gamma is not a constant. In this particular case, we're sort of in a crappy situation because look, we have to integrate over the particle time, but the thing that you have to integrate over has the lab time there.
We can swap it out with our time dilation.
Well, what you can do is that you can say, well, TLab is again this expression.
Well, but
So you're going to integrate. You got a derivative within an integration. It's not wrong. It's correct actually. But
doesn't help us.
but maybe it's a little bit easier if you just make sure that all the T-labs are at the same time as the DT labs, yes, and then do the integration. So you would get d T particle equals, I'm bringing all of this to the other side, 1 minus A lab T lab over C. So I just made the algebraic step that I put all the T labs at one side. And now you can safely integrate both sides, right? DT lab, integral, integral. And if you then continue this exercise, you would get this. That integration is simple, right? This is going from point A to point B. So the left-hand side will become, well, what we used to call delta TB, the amount of time for the total two events. In other words, you get the capital delta here equals, well, yeah, then you have to do this crappy integration.
Not lab.
You are completely right. Thank you. Particle. If we're really smooth, I would say I made this mistake on purpose, so just to see if people were still. So.
Listen.
You're right. Now then you have to do this crappy integral, yes? Now it might be a difficult integral. This one is actually not that difficult. I'm sure you can figure out what this is. And you get some expression. I actually did the integration. I don't think it's that enlightening to write it out. I'm going to write it out just for completeness if I have it somewhere. I'm not sure if I have it somewhere where I can just give it to you directly. Otherwise, just type it into some expression, integrator. Let's see if I still have it. I do actually. So it's not about the answer, it's about the methodology, yes. So this is how you do this. So just for completeness, I'm going to write down the answer. Arc sine A over C. Where I write A, I just mean the A in the lab frame. T lab squared over 2A over C plus T lab 1 minus A lab T lab C squared square root over 2 plus integration constant. This C is integration constant, it's not speed of light. So this is what will come out. Now you can investigate this expression mathematically, but that's not the point of this exercise right now. It's just to show that you can do special relativity on accelerated systems. Yes? By the way, how do you find this number? If you do the integration, you always get plus constant, yes?
Well,
Yeah, but you
what time is, well,
you should know T lab. I mean, maybe you could use high school physics to calculate T lab.
I
it's
agree.
just the time your watch was on when the particles started
Yes.
at A.
In every branch where you have to solve a differential equation in physics, it comes the constants that you get are always fixed by what we call the boundary conditions, the situation at hand. Now, if the situation is such that the particle time and the laboratory time happen to be t is 0 when they started, that means C has to be chosen such that if this guy is 0, that guy is 0. Yes? In this case, that means C itself must be 0. Because the arc sine of time is 0 makes this whole guy 0. This whole guy will also be 0. So at T lab is 0, the particle time will be 0. And if that happens to be a boundary condition, that means you didn't have to add anything yourself. So this number is context related. Anyway, the big point here is not the expression. The big point here again is to show you that the misconception that there is that you can only use special relativity for non-accelerated systems is simply wrong. You can perfectly use it. Look, it works beautifully. Now, going back to the original comment, but yes, this is actually wrong. Fine. Take this guy, stick it in there, and redo the integration, okay? No, it's true. This is how you should do it. Then you have everything physically completely correct, because this argument you don't have to worry about the particle going faster than the speed of light. So, now to finish off this misconception, we now know how you can go from one frame's time to the other guy's frame time. Suppose that we would have done it the other way. Suppose that we would have started with knowing this guy's time, and you would have tried to use time dilation to go back to the lab frame, to the Yakov frame. That would have been wrong. Because this frame, because of its acceleration, is a non-inertial frame. That means that this rule does not apply to begin with. So yes, you can use special relativity in accelerated system, but only in one way, not back. Okay? That is one of the huge misconceptions of special relativity. So if I'm going to, I'm not saying that I'm going to, but suppose that next week you have in your midterm an exercise where something is accelerating, and I'm going to sneakily ask you to calculate the amount of time in this frame to the next frame. It might just be that I'm testing not whether you can use time dilation, but whether you are keen enough to see that something that I'm forcing you to use a rule where it's not allowed. I'm not saying that I'm going to, but suppose that I did. Okay?
So, since this exercise was in the first week,
Yes.
they wanted you to use it wrong.
No.
Or they want you to use it that way, but
No, the exercise unfortunately is a little bit ambiguous. Alisa, do you know the number of that exercise?
I think it was 5.4.
Yeah, I think so too.
Yeah, it's
yes.
Yeah, and I have a
5.4.
book here if you want.
And there's the book. Okay. Well, we can check, but anyway, I think it's 5.4. Now, if you recall, 5.4 in that book, they haven't done any Lorentz transforms yet. They've only done Lorentz contraction and time dilation, and they certainly have not done anything about general relativity. Although they did mention inertial frames in chapters 1 and 2. Now, the way that the exercise was phrased was a little bit ambiguous. They never specified whether the particle is accelerating or not. They do write accelerator. So if you read the exercise and think, oh look, something must be accelerating, they should have been a little bit more clear in their phrasing. What I think that they mean is that the particle was accelerated, and from that moment on went with constant velocity. That's what I think that they meant.
I don't think so, because it says the final velocity is about blah blah blah.
Oh, they do?
Yeah, so I think it's like saying that it is accelerating.
Okay.
yeah, because I didn't like these.
Yeah.
No, that wasn't.
I don't.
Okay, so just to be sure, the issue, if any, does not lie in the physics, yes? It lies in what did they write down and what did they mean when they wrote it.
But
Anyway.
they also say assuming the velocity stays constant. So.
Yeah, so okay, so if they say at the end the velocity is such and such, but they also say the velocity should be constant.
Oh, yes.
So then it's accelerated to a final velocity, and then it stays constant at that final
Yeah,
velocity.
but in order
While
then to do the
traveling
exercise
through
correctly, you have to know whether it reaches final velocity already here or here, because it really changes the exercise.
Yeah.
Yes. Or changes the numbers that come out. The methodology is still the same. Anyway, all of this is that 5.4 could be phrased a little bit more clear.
But Gideon, when you're saying, you may or may not put such an exercise into the midterm just to see
Yes.
whether we know how to apply it, or
No,
then it
everybody,
shouldn't.
this is
it
a question
shouldn't.
about what I'm going to ask next week. Yes, but
So if you put something like that in there,
Yes.
do you actually expect us to solve it and just be like, oh, this can't be solved using normal Lorentz contraction? I'd have to integrate over stuff.
No,
I can't be bothered to.
Without saying too much about the midterm next week, I phrase my exercises such that I first let you answer whether something is an inertial frame. And that should give you enough of a hint, yes? I mean, if you have first identified whether something is a non-inertial frame and you still make the mistake, well, then you deserve not to get the points. Okay?
Well, I mean,
No,
but
not
in
him,
this
but
case, I
generally
mean, we
speaking.
can do it, even though one of them is not an inertial frame.
Yes.
So it's still solvable.
It's still solvable from the non-inertial frame.
Yes.
From the inertial frame to the non-inertial frame,
Yes.
not the way back.
So if you ask.
Oh yeah. Oh okay. All right.
All right.
But
So, everybody clear on this part? Yes? Good. Now, let's do another misconception. So I consider this a closed matter by now. Going to keep this here for the people who want to see talk Jocko about special relativity. No, it's fine, it's fine. I talked about particle physics for a bit, so I guess we can swap expertise every now and then. I'm joking, I like Joko. Before the break, let's do one other thing that people might get confused about, or people do get confused about, and those are those paradoxes, where it seems as if special relativity contradicts itself. We've already seen a couple of them during the exercises, right? Most notably the Sun-Gliese exercise 4.7 that we did in full detail. We showed that if something is traveling from here, from that wall to the other wall, and you ask him how long do you think the traveling guy that the other guy says that you took, your number comes out different than his number. So I'm not talking about my watch giving you a different number than the people who were back at the wall, the Sun people, right? Just for everybody to remind yourself, the exercise had something to do with Sun, Gliese, spaceship, flying all the way to the other side. I, the spaceship person, look how long that took me to fly to the other side, and will come up with a number. The people at the Sun will come up with a number. Those two numbers don't agree. That's not a paradox. That's just special relativity. Right? That the amount of time from one frame to the next is not the same. The paradox lay in if you would then ask me what I think that the Sun people measured, that I get a different number than they themselves. So it's not so much a paradox that my number and their number don't agree, my watch and their watch. The paradox lay in the fact that if you would ask me what their clock reads, that number and their own clock do not agree. So it's a statement about the same clock and those two numbers do not agree. That was a paradox. Do you recall what the resolution was to that particular paradox?
Simultaneity.
Loss of simultaneity, yes? It's because the people on the ship, when they did their measurement how far they had traveled compared to the Sun, said that they did their measurement not at the same time when they arrived. And that change in amount of seconds was exactly what was missing for our clocks to agree. So there was really no paradox. It was just a misunderstanding of when did the measurement happen. So that's a paradox about time. Here's a very famous paradox that I'm going to show you now. You might have heard it before. It's called the ladder and barn paradox. Just to be sure, has anyone ever seen or heard about this particular one before? It's a very famous one. You have? Can you recall what it was?
I wanted to ask you about.
Okay, you had a question about that one?
Yeah, sounds great.
All right. Well, but
Or
maybe
is it the one with the light going? No.
nobody else knows this one?
What page was it on?
Let's go through it. It's as follows.
It has pictures, so you can find it.
Is it the rhino one?
This is my artful rendition of a ladder, yes? It's a ladder, somebody's carrying it under his arm. Maybe for talking's sake, let's say that this one, somebody holds it under her arm. Let's make this a woman, so I can talk about he's and she's, and we understand who I mean when I say person X. In fact, let's make this a farmer's wife.
Very sporty,
Best I can do.
very quick. Just the conditions.
Yeah, okay, well. It looks as if she's leisurely walking to the other side. Let's say that her leisurely walking is close to the speed of light, okay? Now,
It's a brisk pace.
it's a very brisk pace, this one, yes. It's what countryside does to you, yes? In Amsterdam, we don't walk that fast, but on the countryside they do. Now, there is also a barn. And the barn, let me draw it like this, is, I have to come up with some numbers, but let's say that the barn is 15 meters wide. The ladder, unfortunately, is 25 meters wide. So the rest length of the ladder is 25 meters, and the rest length of the barn is 15 meters. So, in other words, the ladder will not fit the barn. Fortunately, the farmer, not walking at all, just standing still next to the barn, will have thought, you know what? If I know my special relativity well, then that means, I don't know if people are snickering as if farmers do not know relativity, okay? This farmer will say, you know what? He asks his wife, if you increase your brisk pace, in such a way that you, compared to the barn, will have a velocity that is close to the speed of light, whatever the number is. The farmer will say, that means, according to me, the ladder will have shrunk to a shorter number. Right? That's Lorentz contraction. So that means that if you just run fast enough with the right velocity v or higher, that means the ladder will have shrunk, Lorentz contracted enough for the ladder to fit into the barn. Great. That means we can now fit the ladder into the barn, which is good. It starts raining, not half of your ladder will get wet. But the farmer's wife, also being somewhat of an expert in relativity, will say, no, wait a minute, whoa. If I start walking with high velocity with respect to the barn, that means in my frame it will be the barn that is Lorentz contracted. So it will not be 50 meters, depending on what v is, it will be 10 meters or so, 7 meters, 9 meters. It will fit even less. This is a paradox, because if you ask the farmer, if you set up this situation, will the ladder fit? The farmer will say, yes, it will fit. But if you would ask the farmer's wife, will it fit? She will say, no, the ladder will not fit. That is a genuine paradox. Because obviously, physically speaking, either ladder will fit or it won't. Agreed? So the question is how to resolve this one. Yeah, please go.
It's not exactly the same problem as the one that we use to...
Chopping of the head?
Yeah.
Yes. It is, well, the resolution is very close, but not everybody was doing that tutorial. But yes, the resolution is very close.
Because, yeah, to me it seems to be basically the same issue, and therefore the loss of simultaneity would make the one wall appear to, like, the ladder reach the wall later.
We're already there. Now for the people, he's referring to one of the tutorials of last week. It was you, right, who came up with this, with the chopping of the heads?
Yeah. Mm-hmm.
Yeah, okay. So for the people who were not doing, were there during that tutorial, there is sort of a loss of simultaneity going on as well here. You see, you have to think really clearly of what it is that you mean when you say something fits or does not fit, right? When you say that something fits, what you're saying is that this front end is within the barn, while at the same time the back end is also within the barn, right? When I say that something fits, I mean that both ends of the full width of the thing are both of them, in this case, within the barn. Then it fits. At the moment that I'm going to measure where the front end is, I also have to measure where the back end is. That will not happen at the same time for both observers. There's something we picked up last week, that there is something called the loss of simultaneity. If you ask one of the two observers, does the ladder fit? You're really asking that other person, please measure the front end and the back end at the same moment in time. Take those two numbers and see whether the difference in meters between those two numbers is smaller than 15. But the premise of the question, please look at the front end and back end of the ladder at the same moment in time, that premise does not hold in both inertial frames. If one of them says, I've measured the front end and the back end at the same moment in time, the other observer will say, no, you didn't. You measured the front end first, and only then did you measure the back end. So obviously you might get a wrong number. So that's the resolution. The rest is just putting into the Lorentz transforms. Do you see, I mean, without having gone through the exercise, do you see where the issue was here? Do you see that the whole issue has to do with how do you define something fitting or not? That it has to do with measuring front and back end at the same time. Here's the key point. Same time doesn't have the same meaning in both of the two frames. That's the paradox. Yes? Now, this is going to be an exercise in the tutorial later today, that you actually go through the exercise. So I've already given you what the solution is. I just want to be sure that you can get the numbers out. Now, what would you do to resolve the exercise? So don't give me numbers, give me a methodology. What would you do to show that there is really no paradox? Suggestion is welcome.
Could you apply the same thing we just previously did and do it from both frames? So do it as the lady being the lab and the bar and the particle, and then also the other way, and then maybe see where the difference is, if there is one.
You will find a difference.
Yeah.
If I would have given you an amount of velocity here,
Mm-hmm.
you will find that one of them will say that the barn is shorter, and the other one will say that the ladder is shorter.
Mm-hmm.
So that means that there is a difference in fittingness.
Yeah, and then we
Yes.
would apply what we did 2 tutorials ago, which was adding the difference via using. Do you guys?
I find
Anybody help me?
there's good stuff there, and
Okay.
the answer, without having seen the application, without the full implementation, the answer is correct. Yes, Louis.
But if you're measuring both ends at the same time, and there's no delta t, right? It's instantaneous, so you can't really use standardization to resolve this.
No, but fortunately we have formulas that do not require you to measure things at the same time, or at the same position. You're referring to time dilation, this formula.
That was the,
Yes,
well, yeah.
but we have more elaborate formulas now. We derived them last week.
Oh, yeah.
Lorentz transforms.
Yeah.
Now I'm going to go with Raquel because she in her wording, you obviously have to do the implementation in mathematics. That's going to be your job this afternoon. But you have to calculate how many seconds there is a loss of simultaneity. If you ask the farmer, did you measure the front end and the back end of the ladder at the same moment in time? He will say yes. But if you then ask the farmer's wife, and you ask her, did your husband measure the front end and the back end at the same time? She will say, no, no, no. According to my watch, he measured the front end and only later measured the back end. So that means, according to her, she saw her husband first measure one end of the stick, then waited a second or two, and only then measured the back end of the stick. So she will say, of course you get a different number for the length. You did not properly measure front end and back end at the same time. It's even better than that. She also knows exactly how many seconds she saw her husband wait before measuring front end and back end. So she knows exactly how many seconds her husband was late in measuring. That's the loss of simultaneity. So what will she say? She will say, I'm sorry, my dear husband, you measured a couple of seconds too late or too early. You have to do the exercise to find out. But you did not measure front end and back end at the same time. Therefore, you were a couple of seconds late. So therefore, you missed part of the length of my ladder. How many meters did you miss? Well, the amount of seconds that you were late times how fast the stick was flying. You can calculate that number. And that number, what she sees that he missed by measuring too late, that number added to her own should then give the same number back for both. So if you correct for the fact that as from her frame that the two ends were not measured at the same time, if you correct for that as seen in her frame, all the paradoxes should disappear. Now this is going to be your exercise to do the numbers, yes? So it's loss of simultaneity. So it looks like there's a paradox. The ladder will fit or it won't fit. But it turns out it's just that the farmer and the farmer's wife do not agree on whether the farmer did his measurement correctly, whether he measured the front and the back end at the same moment in time. Yes? The rest is just doing your Lorentz transforms. You should be able to do this by now. We're going to practice this during the tutorial. So, to wrap up this first part of today's lecture, we've looked at two paradoxes, two things that people can get wrong. One of them is not taking into account all of relativity, like the ladder and barn paradox, where you miss, if you're not careful, the loss of simultaneity. And the other one is that you might accidentally apply special relativity where it's not allowed because things are accelerating. Those are the main two mistakes people make when they try to apply this and they find numbers that do not seem to make sense. Yep. Now we're going to have a break. After break, we're going to do graphics. Right. See you in 10, 15 minutes.
Okay.
All right. People, let's get started again.
Yeah.
So, one of the two learning goals for this week has now been crossed off. We've looked at two of the misconceptions and paradoxes that you might find yourself into. Again, in the tutorial, I will let you work through the actual exercise and see if you can resolve paradoxes yourself. I can promise you this, in all seriousness, at the midterm, I will ask you a paradoxy exercise, where I will say, calculate this, such, such. There's a paradox, please try to resolve the paradox. Right, where you first have to do it verbally, say, oh, well, this is going wrong. And then there's an additional follow-up exercise where you actually have to perform the numbers to see that everything checks out. So this exercise that I just gave you verbally what the issue was, working this out in the tutorial today is going to be important. Now, it will not be the exact same exercise, I'm sure you understand, but it is a similar one. So learning how to do this exercise with the ladder and the barn, and also the San Gleason one, really is something that will prepare you quite well for the midterm. All right. So with one learning goal crossed off for this week, let's go to the graphical part. Now, if you do normal Newtonian mechanics, I'm sure you can do it using formulas, right? You get all these crappy formulas, something like this. This is not the one that I want. Let's see if this one works. Yes. Right, you get all these formulas. I'm sure you know from high school and blah, 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 right?
If you want
Oh,
something.
actually, thank you so much. Great, great, great. Yes. This also really helps for midterm, by the way. And the same with cookies, by the way. No, he told me that I could have one, so it's actually my fourth in my inertial frame.
This is
If you know how to do your normal classical Newtonian mechanics, then you know your formulas, right? You know how to do this sort of stuff. But you also know, if you want, how you can write this in graphs. Right? You say, well, this is time, here's the position of something, and if it moves with a constant velocity, it will probably look like this or something like that. If it has a constant acceleration, it might look something like this. That's actually this formula, like it's parabola. So you can do your Newtonian physics both in formulas as you can in graphs. And sometimes graphs are even somewhat simpler, because literally in one beautiful visual sight you can see what issues are. Suppose that I have something that moves with a constant velocity, like this guy, and that he started at position 4 meters. And suppose that I also have an accelerating guy who started at a position of 2 meters, and I ask you at what point will the accelerating guy gain on the other guy. You can immediately tell, oh, that's over here. At this moment in time is where the accelerating time will move past the guy with the constant velocity. Whereas in formulas, it's a little bit more difficult maybe, right? This guy is this one, that guy is that one, and when do they cross each other? Well, when this delta x, maybe that delta x or something like that, and then you solve for delta t, these sorts of things. So you can do Newtonian mechanics in both algebraic way, formulas, and in a graphical way. Now, what we have done up to this point in special relativity is only done it in an algebraic way. Ultimately, we started with this invariance of the Minkowski line element. From that we got our Lorentz transforms, and we've now been using Lorentz transforms for every single thing so far, yes? But it would be so nice if we could also do it graphically. That's what we're going to do today. They're called Minkowski space-time diagrams. They're really just diagrams like this, where you can see the amount of time and the amount of space covered by an object in a graph. But maybe you can already imagine that the graphs are going to be a little bit more difficult to read and to interpret this time around. Do you recall last week when we talked about normal Euclidean space where Newtonian physics lives? Mm-hmm. That it came with this very special rule. Right, that if you wanted to know the amount of distance from here to there, you need to know how many meters in x direction and in y direction, and you do Pythagoras theorem and such. There was a property of the space itself on which you try to apply Newtonian physics, right? But we also saw that in special relativity, you have a similar rule, but you found that not this number is invariant, but this number is, including the minus sign. And it's the minus sign ultimately that gave us the Lorentz transforms. It's also the minus sign that will make our graphs not look like these. They're going to look different. And it takes a while to get used to it, but once you've gotten used to it, so it's sort of a learning curve, but once you've gotten used to it, you will actually find that some of the exercises become more clear. Maybe not in the numbers, yes? If I were to ask you to, in Newtonian physics, to make a graph like this and just read off what this number is, you're probably going to make some read-off error, right? Depending on how good you drew your picture and how big your magnifying glass was to find out what this number in time was, you won't get it exactly. So there's a drawback in doing it in graphical way, read-off errors and such. But there is something good, and that is that you can immediately see where what happens just on glance, one particular glance. The same plus and minuses also apply with Minkowski space-time diagrams. If you want to do the read-off, that is a little bit difficult. You have read-off errors and such. But if you just want to know what's going on, that's very simple. Because you can immediately say, oh, well, there's where this happens, there's where that happens, here's that event, there's that event, that takes so much time for this guy, takes so much time for that guy. So this is really going to be a really helpful tool. Not to get the numbers right, but to get your insights right. So having this tool to your disposal is really going to help you. So let's go through it. Now, special relativity, as you know, always has to do with how much time passes in one frame compared to how much time passes in some other guy's frame, and how much distance is there in one frame compared to some other guy's frame. So that means we have to find some way to take one guy's space-time axis into some other guy's space-time axis, right? In Newtonian physics, that is very simple. Suppose I introduce a new coordinate frame. I'm going to draw it in red. Forget about these lines for a moment. Just about the space and time. Sorry, space and time. And I'm going to introduce another observer who's moving, and let's say for the sake of simplicity that the other guy is moving with a constant velocity compared to this black frame. So there's another coordinate frame here in red. Let's put those primes. And this red coordinate frame is moving with constant velocity with respect to the black frame. It would look something like this, right? With every second, the red frame will be a little bit shifted to the right, shifted to the right, shifted to the right. And that also means that if you have two events, two things happening, for instance, here's something that happens and here's something that happens, you can immediately see whether it takes more or less meters between the two, as seen in the two frames, agreed? Bigger or smaller number in the red frame than in the smaller, right? In fact, this is the trick we've been using to see whether you should use a plus or minus in the Lorentz transforms. But this is quite simple. The amount of time is the same, right? So no problem there. So in Newtonian physics, making these space-time diagrams so you can compare red frames to black frames is actually quite simple. Now let's go to Lisa. I lost your marker. This one?
I have more.
It's this one. Okay, thank you. We'll get it back. Minkowski space-time, things are a little bit more complicated. Now, let's just define the black frame here. Now, for reasons that only have to do with historical convention, in Minkowski space-time, we write the time axis vertically and the space axis horizontally. Why? Reasons. There's no physics there. It's just historical. So this is space. Yes. This is time. Again, for historical reasons and also a little bit pragmatic reasons, the time axis is now always written with an additional c in front. You don't have to, but this is historical and conventional. But can you see that this is pragmatic to do it in this way, to put a c there? Can you maybe tell me why there's a point here?
To get the same units.
To get the same units, to make sure that the units are the same. This is very much the same that we had here last week, that we said you cannot just have the dt squared and the x squared, you are missing a velocity. So you have to squeeze a velocity in there. Okay. That's very much the same here. You don't have to, by the way. You can also just drop the c. Sure, then you have two axes don't have the same units, but then again, we also did Newtonian physics. No problem whatsoever. You can still draw the pictures. It's just with the c, you will see that the pictures have a certain amount of beautiful symmetry that would come out. You will see that in a moment. Now, let's look at a couple of examples of things happening. Suppose that you have something moving with a constant velocity in the black frame. How would you draw that?
Straight line.
No, straight line, like
Directly
vertical?
upward? Something like this?
No, in the other, no.
Like this?
No.
No.
In between.
Yeah, just a straight line in between, yeah.
Below the line of x is y.
Yeah, sure.
Yeah.
Okay. Yes, agreed. Of course, this is a straight line. Yeah, this is constant velocity. If something is standing still, as seen by the x guy in the black frame, how would you draw something that stands still, doesn't move at all? It will be like this, right?
Mhm.
At any moment in time, it's at the same x, etc. Good. Fine. Easy enough. If something goes with the speed of light, how would you draw that one?
It's also a straight line that's at some angle.
The line x is y.
The line x is y, agreed. That's the reason why we put the c here. Because by having this c here, we've made sure that the speed of light line, first of all, it's a diagonal straight line because it is a constant velocity, but it's a 45-degree line. It's 45 degrees. I did not draw it quite nicely, but it's 45 degrees. Without having put this c here, but any other number or no number at all, you would still have had a speed of light line, but it would still have been a straight line, diagonal straight line, but it would have had a different angle. So it's just out of wanting to have a 45-degree line corresponding to the speed of light is why we have chosen to put the c there. Good. Now, I'm going to remove all this because that was not our question. The question was, what I now want to do is introduce some other guy moving with a constant velocity with respect to this guy. How do you draw that guy's coordinate system? Does it look like this, maybe?
Tilted, no?
What do you mean tilted?
Well, it depends where he is and how he's positioned.
Well, let's say that the two guys they start with the same origin.
Wouldn't it just be like rotated by a couple of degrees?
As in the whole thing will be rotated, so the red one is like this, something like that.
I mean, I didn't think about it much, but seems right.
Well, let's think about it. Okay? Keep making the same mistake. There we go. Let's define those two new red coordinate axes. So, in fact, let me keep the color coding. I think that's easy to look at these things. Let's first define the x prime axis. The definition of an x-axis is, well, the line where the time in that axis is 0, agreed? I mean, the black axis, x-axis, is by definition the line at which its time is 0 throughout. So you can play the same game. It's just the definition of the axis. You can play the same game with defining the red coordinate axis, x-axis. But the question is how to draw this in this frame. It would be really great indeed if we would have some sort of functional form, that if we would have this guy's time written as this guy's x, y, well then I know exactly using my basic high school mathematics how to draw that line, where this right hand side will then be by definition the x primed axis. Do you see what I mean? I'm looking for the x primed axis, but I want to express the x primed axis as a function that I can draw in the black axis. So I know exactly how to draw it.
Lorentz transformations?
Yeah, that sounds good. I mean, if there's one thing that Lorentz transformations tell you is how to express one guy's time and space into one other guy's time and space, right? So let's immediately do that. You have that the t prime is gamma dt minus v over c squared dx. We derived these last week. Please check me on my c's. As you know, my c's in my mind are always 1, so I tend to forget some here and there, but I think this is correct. All right. Now, as you know, Lorentz transforms say something about a duration, about a distance in time and a distance in space. It's about a dt and look, I'm being sloppy here now. There you go. It's about dx's and dt's and not about t's and x's. But you know, if we just define one of the 2 points in this duration and one of the 2 points in this distance to be exactly at the origin, then that means I might as well write this. Now, t. Right, Lorentz transforms say something about the duration. This moment in time minus the other moment in time. But if one of the 2 moments in time happens to be at 0, then a dt is simply a t, right? So what I've done now by going from here to here is that I've defined where my origin is. I've defined that the origin of one of the 2 points is exactly at 0. Unfortunately, sometimes in books they write Lorentz transforms always without the d's or the deltas, which is fine, but only under the assumption that one of the 2 points is at the origin, which is not always the case. We've seen examples where it wasn't. But we are now making the choice that this red coordinate system will have the same origin as the black one, and therefore these Lorentz transforms go into these. Now, so we have our Lorentz transforms, and as we were just saying, the definition of the red x prime coordinate system is when the t prime is 0. So, what I'm writing down now, this equals 0, is saying I am now defining my x prime coordinate system, my x prime axis, yes? So this point is the definition of x prime axis. That's what we have. Good. Let's continue with that conclusion. We have now a definition for where the x prime coordinate axis is. Now, you immediately see that if this is 0, you might as well divide away the gamma. You don't have to worry about dividing by 0. Gamma is never 0. It's 1 or bigger. So you can easily define that away. And I get t minus v over c squared equals x. Should be 0. So what I get is that t as a function of x equals, goes the other side, v over c squared. Yes. And because we have decided to write our time axis always with an additional c in front to get the units right and to have a beautiful 45-degree line for light, you put an extra c here, cancels that one. So what do I have here? This equation, which is an equation in the black coordinates, is how mathematically the x primed in the red coordinate is defined. Yes? So if you would draw this line, in this picture, you will have your x primed axis. So let's draw it. Oh, I was missing an x. Sorry about that. There you go. Good. Now, if I'm not mistaken, this is a straight line, right? I even know what its derivative is. It's v over c. This is how much it goes up. So it's a straight line, and because we went from here to here, we have to find that it starts at the origin. Right? This is how we got from there to there. It's a line that looks like this, a straight line.
It's going fast. I know it's the axis.
You can even say what this angle is. Call this angle beta typically. Because look, you can easily see that there is a triangle here, right, with this beta here. And this distance, that will be a dx, or because you start in the origin, this is just x. This is c dt, right? Then you use your, again, your high school physics, means that the tangent of this number is ct over x. Yes. But ct over x, well, ct over x just means v over c. So what I find is the tangent of beta is v over c. In other words, this beta is the inverse tangent of v over c. So we know exactly where the x prime axis is. If I tell you how fast the red coordinate system is moving with respect to me, I give you v, the number. You take the inverse tangent of that number, you get beta, and you can draw the line where the x prime axis is. That's all there is to it. It's very different from here, by the way. If you went to a red coordinate system, sure, there was some shifting maybe, but they certainly did not tilt. So here's really where you see special relativity differing from Newtonian mechanics. Now you could play the same game with defining the t prime axis. I'm not going to write it out. You can easily do this for yourself. But the t prime axis, how would you define that one? T prime, we have the x prime, this is solved. How do you find t prime axis?
90 degrees from the x-axis.
Something like this?
Yeah.
This was a suggestion we heard before, right? It rotates.
I think it's actually going to be squished together because you have to keep the speed of light constant, but I didn't think about that in the beginning.
Because then the speed of light would be different.
I'm very happy with the suggestion because you would think that, hey, space and time should have an angle of 90 degrees, right? So if we have the x prime axis, then the t prime axis should also be 90 degrees with respect to that. So you'd think that it would be something like this with the same beta here. Unfortunately, that's not the case. And the reason ultimately lies in the fact that we went from Euclidean physics to this new type of, Euclidean geometry to a new geometry that happens to have this very strange minus sign that accounts for special relativity. If this had been a plus, you would have been completely right. So we have really, because of the strange rules of space and time in the Minkowski picture of special relativity, things look different. So we have no choice but to define it in this formal way that we also do with the x prime axis. The t prime axis is by definition when x prime is 0. Agreed? So that means you now take this equation, set it equal to 0, and then turn this guy into a red line in the black system. Now you can easily do that for yourself. It's very much the same exercise, but the steps are simply this. You now set this equal to 0. Setting this equal to 0 means it's by the definition the t prime axis. In fact,
But can't you make it much easier and just argue, oh, the speed of light still has to be a 45 degree also in the nuke system, so the angle has to be inclined at angle beta again,
ultimately,
just squished together?
Ultimately, this is of course what you will find. So you could have even done it that way. In fact, one of the exercises during the tutorial is to show that no matter in what axis you go, you will always find the same speed of light, that the speed of light is invariant. Now Felix now is making the opposite argument. He says, well, given that the speed of light should come out the same, then how should the other axis look? Both work, yes? It's either you go from A to B, or you start at A and you find B, both work. Now, I am going to take this particular route. The steps, again, are very much the same. If you do that, leave that for yourself to work out, you will get that this one is also tilted inward. And you can, again, find what this angle is, and you will actually find the same angle. Don't take this from me as a postulate, just go through the mathematics and you will find that this is a necessary consequence of the Lorentz transform. You have no choice but to conclude this. So what you have here now is CT primed. So we now know exactly what will happen if you go to some other guy's coordinate system. The space and time axes will curve towards each other. They will rotate towards each other. Exactly in the middle is where you have your 45-degree line. That's the speed of light. Okay. Now, this is how you find your axis. Again, if I tell you how fast the red system is moving with respect to the black system, you can calculate beta, you can draw this picture, and you can see that they are rotating towards each other. Yes?
Is that like another way of saying that you can't go past the speed of light because your beta can be more than 45 degrees?
That is a good question. At the moment that you go with the speed of light, you make v equal to c, you get the arctangent of 1, which is indeed 45 degrees.
Yeah.
So there you go. So it means that if the faster you will go, the red system will be closer and closer to the speed of light line. And at some point, they will find each other, which strongly suggests that this is the faster you can go, because from that moment on, space and time will swap places or something like that, right? They will go past each other, and what the hell does that mean? But there is it strongly suggests that something goes on there. Now,
Well,
let's. Yes.
And this is just the red coordinate system as viewed from the black coordinate
Yes,
system.
that's absolutely correct.
Okay, just
Yes. So that's all clear, yeah? Now, this is how you find your red coordinate system. Now let's do some measuring. I need a timekeeper. How, 15 minutes?
Yes.
Good, okay. That's perfectly on time. Yes.
If you're in the red coordinate system, do you see the black one the same as when the black one sees the red one?
Yeah, that's a good question. If you are in the red coordinate system, how do you see the black one?
Yeah.
Right? I'm going to show you now. That's exactly the next point. How do you read off events from here? Let's take 2 events. Well, you know what? Let's start with 1 event. Let's make things simple. Let's take 1 event. Something happens. And as you know, my prime example is an exploding firecracker or something like that. Great. You know what? It explodes here. So the green is an event, right? An event is something that happens at one position in space and at exactly one moment in time, which is very approximately true for a firecracker that explodes. And the question is, at what moment in time does it happen in the black system, and at what moment in time does it happen in the red system? Now the black system, you can ignore the red system for now. If you just want to know where this thing happens in the black system, you just use your Newtonian way of reading off where things happen. If you want to know where it happens, that's simple. Well, it happened here. Some number, yes? So thing explodes over there. This is the origin. So here's me seeing over. You see one of your codes explode. And then this is like 3-4 meters or so. All right. Now, when does it explode? Well, if I have to find that now is now, t is 0, and 2 seconds later your code explodes. When do I see it explode? Well, after this amount of time. From my t is 0 moment. So it's very easy to read off when things happen and where they happen in the red system. Question. Where and when do they explode from another coordinate system? So there's another guy walking towards your codes and he sees your code explode. I don't know who brought their firecracker in their codes. So it's the same explosion, so it's the same green dot, it's the same event, but you have to read it off now on the red axis. Forget about the black axis now, we're talking about the red axis. Going to make a suggestion. How about this? That's where it explodes?
I don't want to seem elementary, but what I would do is trace the line to X, but as seeing it like as that's the point. So instead of just like, since X is like this, the red X is like this, instead of going from here to there, go from here to there. So seeing this horizontal.
Measure perpendicular to the axis.
Yeah.
Mm-hmm.
I don't know if that's right.
Perpendicular to this axis? So
Yeah.
To the red axis.
Well,
Yeah, to the red axis X
axis.
and then to the red axis of CT.
Okay.
But then your time transformation would be
but
the wrong way
you do
around.
know that 90 degrees does not work anymore, right? We've met what the 90 degrees with the angles here.
I don't understand.
Well, yes. you.
Go parallel to the axis of the CDF.
How about that?
What axis?
Ah, yeah. Correct.
Parallel to the axis that you're not worried about. If you want to know, just like in the black system, you just have to drop downward, yes? Dropping downward is another way of saying parallel to the other guy's axis. Or not, sorry, not the other guy, but your other axis. You can do the same here. Take that line. So,
I mean, that's basically what you were saying. Just
But the opposite.
No. Just that perpendicular in the red system doesn't mean 90 degrees anymore.
Yeah.
You are going perpendicular.
Yes.
In fact, you're just 90 degrees on.
That was my answer as well. That the 90 degrees rule does not work anymore.
Okay.
So, what you do in Newtonian physics, Euclidean physics if you want, is that you indeed go for the 90 degree angle.
Yeah.
But 90 degrees is now messed up due to the beta, so the best thing you can do is go parallel to your other axis. That's what we're doing.
Thank you.
Alright, so it is this moment in space where it will happen. Now, note that this makes sense, people, because do you see that this is a shorter distance than the black one is? Does it make sense that if I walk towards a thing and then I explode and then there's less distance for me because I was walking towards it? That's just what you're seeing here. Okay? So it's really not that strange that you find that on the red axis is a smaller number than it is on the black axis. There's a subtlety there that I will get to at the end. Yes, just visually you can see it should be a shorter distance, and it does come out as a shorter distance. Now, same question, but now for time. At what moment in time does the guy walking towards the code see the firecracker explode? So I want to know the position on the red time axis. How do I measure that one out?
It's the same thing, no?
Same. Parallel to the x prime.
So okay, so this guy, parallel. Yeah, this is note to self. Bring me one of these big rulers. Okay. There you go. For the red guy, this is the amount of seconds that it takes before he sees the firecracker explode. So what is the upshot here? If you want to read off your red axis, right? You know how to draw them now. They just give you V, you can calculate beta, you can calculate where the red axes are. You also know now how to read off times and positions in the red coordinate frame. That's easy enough. Now, that's almost all there is to it, but there is a subtlety. Yes. And the way that I want to introduce this subtlety is looking at one of the examples we've seen many times over. I'm going to use that example, Lorentz contraction. And you will see that if you then apply these rules, you seem to come out with the wrong conclusion.
Sorry, can you repeat that?
Oh.
Another thing that I would find, never mind. So stop. Time and space are independent. So like, if he sees it before, like if he sees it closer to when he sees it.
Now clearly, if you actually want to use these Minkowski space-time diagrams, that's how they're called, if you want them to be drawn beautifully, you either have to bring a ruler, because I'm now being sloppy, yes? Obviously, if you want to have real, well read of numbers, you have to make sure that it's beautifully drawn. Fortunately, there's these pre-printed Minkowski space-time diagrams worksheets that you will get from me for the exercises. Okay, you will also get them during the exam. So you never have to draw these things yourselves, because you see how easy it is to accidentally draw them a little bit sloppy and then you get your numbers off. Now, again, what I'm going to do now in our remaining so many minutes is I'm going to show you that there is still something missing from our interpretation of these graphs. And I'm going to show you by showing you a conclusion that is different than what we have seen before. So something is still missing, and I will tell you what that is in a moment. Let's look at the example that is Lorentz contraction. Yes? We're going to look at Lorentz contraction. We're going to look at the length of a stick as seen by the person in the black coordinate frame and the red coordinate frame. So I'm going to draw a stick, which I have to make a choice somewhere. I'm going to choose that it is at rest with respect to the black frame. Yes. So in a situation with the farmer's wife, the black one is the farmer's wife frame. Here's the stick. Has a certain length. L0 as measured in the red frame. Excuse me, in the black frame. Now, I want to know what the length is of this stick as seen in the red frame now. What should I do? How do I find the length of this stick as measured in the red frame?
You like this parallel to the T on the red frame?
Oh yeah. You would say, well, here's one end of the thing, and here's the other end.
Yeah, so you take the other end and you go parallel upwards.
Sure. You would do something like this,
Yeah.
right?
And then
Okay.
you-
So you would say, here's the length of the stick as measured in the red frame.
I would do it the opposite again. I would go like this.
Well,
It's shorter.
well, first of all, the length of the stick seems to come out longer,
Yeah.
but that's because there is something still missing, right? That's what we're working our way towards. No, but there is a different issue, because if you are in the red frame and you see a stick fly by and you want to measure what its length is, when do you measure the front and the back end? Simultaneously, right?
But it's not simultaneous right now.
They're not simultaneous because what you're doing now is that you're looking where the front end is. Yes, that is on your x-axis, right? Your red x-axis, but you're looking where the back end is.
And it's not.
When it's not on your axis. So that means you are not measuring, the red person is now not measuring the front end and the back end of the stick at the same time. This is not loss of simultaneity, this is just the farmer not doing a correct measurement of what he means by length. So, you have to measure the front end and the back end at the same moment in time. Now, fortunately, so the same moment in time means that that this green dot has to be on your red axis. It isn't. It's below it. Yes. You can look at the green point from your axis, but that's not what you mean. You want it to be on your axis. Only then, for the red person, are you measuring front end and back end at the same moment in time. Only then are you making a correct measurement of length. Again, this is not loss of simultaneity. This is not Lorentz contraction yet. This is just you doing your measurement correctly. Now, fortunately, the only thing that the guy in the red system has to do is to wait. Because 1 second later, the stick, which is at rest with respect to the red system, will have moved a little bit upward, hasn't it? 1 second later means in the black system that the stick is still at the same location because it's at rest in the black system. It's just 1 second later in time, right? And 1 second later still, it will be here, it will be here, it will be here. So this line and that line is how the stick moves through time as seen in the black system.
So then okay, if I get this correctly, then for the black system, it's still going to seem as if the red system waited between the two measurements, but for the red system it happened at the same time.
Exactly.
And that's the loss of
That is the loss of simultaneity. So I'm very happy that you're seeing the point. For the people who haven't seen it just yet, let me draw it a little bit more beautifully. Do we all see? Again, just this is the sound of things falling into place?
Yeah.
Good. Okay, great. I told you, once you see the Minkowski diagrams, all of a sudden all these effects that you have seen will become very visual and very easy to understand. Now, for people who are not there yet, let me draw you. This is the length of the stick, yes, because it's at rest with respect to the black system. That means with respect to the black system, it will just move upward. It will not move to the side because it stays at the same position. It can only move upward through time. 1 second later, 2 seconds later, 3 seconds later. Yes.
in the black system, it's standing still, right? She's not moving.
No, correct. And you can see that because at any moment in time where you would ask the farmer's wife where the front and back end is, you will always say the same two numbers. So for her, the stick is not moving. So these green lines here is another way of saying the stick does not move in the black system. Now, going back to our definition of doing a good measurement of length, you have to make sure that in the red system, the front end and back end are measured at the same moment. What does it mean, the same moment, simultaneous? It means when both front end and back end are at the red x prime axis. Only then do you this is the farmer, right? Only then is the red person doing a correct measurement. So the only thing that where's my green one? What the guy in the red system has to do is wait for this side of the stick to hit his x prime axis, because at that moment, this point and that point, the measurement of front end and back end for him happen at the same location, and then he's doing a correct measurement. Yes? So, for the x prime system, it's not these two events that tell you the length of the stick, it's these two events. So that's what's going on. Now, I'm a little bit sloppy in my phrasing because I say, oh, the guy in the red system just has to wait until the stick has moved there. It's by definition he does not have to wait, right? It happens at the same time for him. But anyway, that's just the way that I phrased it. The point here is, a correct measurement means measure front end and back end at the same moment in time. The same moment in time means along this red diagonal line. So this is the event that corresponds to the red guy measuring the front end and back end at the same time. Having done that, it's this distance that is the length of the stick as seen by the red person. Yes?
But how would the red person see the stick moving? So for the black person it moves straight up, but how would the red person see it move? Because I mean,
Well, it moves. It
Does
moves
it
with
tilt?
constant velocity.
you said at first you said he has to wait for him to be on the right axis, but eventually he doesn't wait because it happens at the same moment.
For
in
him,
time. So
yes.
what happens from being horizontal to being tilted to the x prime axis?
I'm not sure I understand the question.
If the wife would measure it at t is 0 for her, ct is 0.
Yeah, so that's
when it's there.
that's along this line. Yes.
In the black coordinate system.
You're right. Yeah, you're right. The wife is the black
Yeah.
one. Yes.
What would it look like then for the red coordinate system? Would it be, I don't know. Or it just kind of
I think I get what you mean.
Yeah.
But like I think the black coordinate system sees the ladder move at the speed, which is the red line. Well, the red line represents the speed at which the wife moves. But like here, you're looking in the coordinate system of the black. That's why your word lines are these arrows are straight.
Yeah.
But then if you want to if you want to change into her, yeah, but that's not possible because then you.
If that's okay, Emma, can we reserve this point for
sure,
the
yeah,
tutorial?
go
No, it's an
on.
important question, and we will address it. For now, there's one final point I want to make generally, and not specific to this exercise. Remember that my narrative was as follows: that I say, well, if you would use the rules that we've seen now with our new axis, you would draw this conclusion: which of the two is the longer one? Who of the two seems to measure the longer stick?
That was
I mean, in a triangle, if I'm not mistaken, the diagonal side is always longer than this one, right? So we seem to have found, if you look at this, that L is now a bigger number than L0. That will be like a Lorentz dilation or something like that. Length has become bigger. Whereas we have concluded in 15 different ways by now that it should have been shorter. We should have gotten this conclusion. Right? So it looks as if something is wrong.
But then you're measuring from two different frames still, right? Because the red L is measured from the red frame. If you do it for the
Yes.
black frame, you'd still have to measure parallel to
Yeah,
to
but,
the axis, right?
but since it's on the axis, it's already there.
I think both the red person, who's measuring front end and back end for him at the same moment in time, and the red person, who according to her system is also measuring, actually I'm messing up my his and hers. This was the farmer's wife, right? So in the black system, front end and back end to her are measured at the same moment in time. Look, they're both at t is 0. So she's doing a measurement correctly, but the red person, the farmer, is also on his axis doing the measurement at t is 0. So for him, it's also at the same moment in time. So both of them are doing their measurement of length beautifully, correctly. Yet, visually speaking, it looks as if this is the case, which is clearly opposite to what we have concluded based on the Lorentz transforms and our thought experiments of week 1.
But there is the time. You have different times.
Yeah.
It doesn't
No, no, no. What you are doing now is that you are saying, wait a minute, yes, but this guy's time is not that guy's time.
No.
But there is
Yes.
a time.
Is it the head thing? That he no,
It has
but
nothing to do with these things. No, look, listen.
I
No,
feel
no, 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 no.
like that-
Both. No, no, no. I mean, what people are now going for is saying, oh, but wait a minute. Maybe that guy or that woman are not measuring correctly, as in they're not measuring front end and back end at the same moment in time, which is true if they look at each other's measurement. But within their own frames, they're perfectly doing everything fine.
Do the axes necessarily have the same resolution?
There we go. The answer is no.
Because
that's
Here's the answer.
fucking
yeah.
feeling.
It gets.
Look, people, there's something evil that went on here. That I could not have shown you based on my crappy drawing by hand, yes? What I've shown you based on these arguments from the Lorentz transforms is that the axis, if you go to another coordinate system, rotate inward by a certain amount beta defined by the relative velocity v, yes? There's something else that goes on. I haven't showed it to you yet. But what also happens is that when you go to another coordinate system, they don't just rotate inward, both the axes, they also stretch. Now, the amount of stretching is, again, one of the exercises during the tutorial. So you will see how much stretching happens. But let me just tell you visually what happens. Let's make some tick marks. Here is, in the black coordinate system, 1 meter. Here is 2 meters. There's 3 meters, 4 meters, 5 meters, 6 meters, 7 meters. Okay? Now, if you look, then this amount of distance, apparently on the black coordinate system, is 1 meter. So if you would take the same, and we use the same distance between 2 tick marks on the red coordinate system, you would have gotten, it will be the red 1, it will be the red 2, red 3, 4, 5. Yes? If that were the case, then indeed this side would have been a bigger number than that side. But stretching happens. By an exercise I will give you in the tutorial, you will find that the number 1 along the axis is not here, and the number 2 is not here and is not there, with the same amount of distance in between successive points. It's a bigger distance. How much distance? Maybe you can already guess what the number is going to be.
Gamma.
Something with a gamma, sure, yes. Relativity means there's gammas all over the place, yes? Yes, you will find that the amount of stretching is actually a gamma. So that means
Just a gamma?
that, no, not just a gamma, there is a specific gamma corresponding to the
Well,
V
yes,
in it.
no, well, yeah.
Okay.
Okay, well, fine.
Anyway,
Is that linear?
now I'm going to draw it a little bit
So
exaggerated.
what is it?
No, I understand, but you will see, okay? I'm going to draw it a little bit exaggerated. The amount of visual distance between 0 and 1 is going to be a bigger distance on the red axis than it is on the black one. So here's number 1. Again, I'm highly exaggerating now.
And this
Stretch. Again, by how much? Exercise and tutorial. But given that that is the case, we will prove it directly from the Lorentz transforms. Do you now see that the red length L is now actually about 3-ish or so? And that in the red frame it was about 5+-ish? and that means that yes, in the red frame, it really is a shorter distance. It's because of the stretching of the axis. The same happens with the time axis. 1 second, 2 seconds, 3 seconds are more visually distance apart than they were on the black one. Again, the amount is going to be gamma. You will find this during the tutorial. So, here's a very important lesson for everybody. If you're going to do exercises using Minkowski diagrams, it's going to sound very negative, do not trust your eyes, okay? Don't think because you know that this is 1 meter in the black system, then the same visual distance with your eyes is going to be the same meter on the red one. On the red one, it's stretched by gamma. If you take that into account, everything will work out just beautifully. So, after the tutorial in so many minutes?
20.
20, good. Then we're going to find out these things in detail, do some exercise with them.
Yeah.
All right.
Okay.
See you soon.
Thank you. Okay,
You're welcome.
because I drew this and